In this video, I'm going to cover chapter 9 of my stochastic modeling book. That's the chapter about Poisson processes and the exponential distribution. I'm also going to talk about Poisson point processes, which is another important topic, but typically not covered in traditional textbooks in probability theory. So more precisely, here are the different topics and results we are going to cover in this video. As usual, as for the previous videos in this playlist, check out the description of the video where you can find the table of contents with the different topics and results we are going to cover and the specific timings, so you can more easily navigate through the video. And at the end of the description, you can also find a link to the file I wrote, the presentation I wrote for this video. Just click on this link if you want to download the PDF file. So the different stochastic processes and distribution we are going to cover in this video are here. These are Poisson point processes, and the exponential distribution. And the main properties of Poisson processes and Poisson point processes we are going to prove are the superposition, thinning, and conditioning properties. So, like I told you, Poisson point processes are not typically covered in traditional textbooks in probability theory. The reason why I want to also cover this type of process is because, in fact, that's a more general version of Poisson processes. We'll see that, in fact, a Poisson process can be viewed to some extent as a one-dimensional version of a Poisson point process, while a Poisson point process is a more general object in multi-dimension. Okay? So that's one reason. And it turns out also that even if those processes are more general than those ones, the superposition, thinning, and conditioning properties not only are also true for those processes, it turns out that because those processes are some kind of special models, they give you some kind of visualization that Poisson processes do not give you, and it turns out that to some extent it's more easy to visualize and even to state the superposition property, thinning property, and conditioning property in the case of Poisson point processes. Okay, so that's the reason why I also want to talk about this type of process. So first, I'm going to define those processes. What do we mean by a Poisson point process, and what do we mean by a Poisson process? And roughly speaking, we will see that a Poisson point process more or less describes the distribution of points that we call Poisson points in space, okay? While a Poisson process describes instead the distribution of occurrences in time. And like the name of the processes suggests, both of them are related to the notion of Poisson distribution or Poisson random variable that was introduced by Poisson. All right, so that's the first step of the video. Then I'm going to move on to a third point of view. When we look at Poisson processes, instead of looking at a jump process and the time of the jumps, or from the point of view of Poisson point process in one dimension, the position of points in space, instead we can look at what we call the inter-arrival times. That's the times between jumps that from the point of view of Poisson point process can be interpreted as the distance between consecutive points on the real line. And so that's going to bring us to the notion of exponential distribution. And more precisely, we are going to prove that the inter-arrival times in fact are independent exponential random variable with the same parameter. All right, so once we know that inter-arrival times are exponentially distributed, some result I want to prove that will become important in the next video about chapter 10, that's going to be about continuous time Markov chain, is the fact that among the set of continuous random variables, the exponential distribution is the only one that is memorious. Okay, so the theorem we'll prove is that if a random variable t is continuous, then exponential is equivalent to memorious. Okay, so that's the next result we are going to prove. And this result, again, will become important when we deal with continuous time Markov chain because looking at the definition of a continuous time Markov chain, we'll see that a direct consequence of the Markov property in continuous time, when the state space is finite or countable, is the fact that the time since the last jump and the time to the next jump are independent random variables. This is exactly the definition of memoryless. Okay? So this result that we are going to prove in this video will tell us that in the context of continuous time Markov chain, because the times between jumps or inter-arrival times are memoryless, then they must be exponential. And this will give us a way to construct a continuous time Markov chain using a combination of a discrete time Markov chain that keeps track of the sequence of states the continuous time process visits, and a collection of independent Poisson processes that describe the times of the jumps. All right, so after defining those three important objects, Poisson point processes, and the exponential distribution that describes the inter-arrival times, we'll prove each of the three properties. So starting with the superposition property. So the superposition property says basically, from the point of view of Poisson point processes, that if you have, let's say, k independent Poisson point processes, each process is going to describe the distribution in space of points with a given color. Let's say process I describes position of points with color I. Then the superposition of all the points of any color is going to be described by a new Poisson point process, but this time with parameter called the intensity, the sum of the intensity of each of the colors. This is the superposition property. I'm going to prove the result for Poisson point processes. Again, because Poisson processes are particular case of Poisson point processes, but in one dimension, we also deduce the result for Poisson processes. I'm also going to give you some kind of dual version of the superposition property for the exponential distribution. This other version turns out to be extremely useful in practice. Then we look at the thinning property. The thinning property can be viewed as some kind of converse of the superposition property. Instead of adding points together, at the opposite, we are going to extract points. This one says more or less that if you have one Poisson point process with a given intensity, and if you color independently each point with color I with probability pi, okay, then if you look only at the resulting points with color I, you end up again with a Poisson point process, but this time the intensity is reduced by the parameter pi, by the probability pi, the probability that a point has color I. Okay, so that's going to be some kind of converse of the superposition property. Together, those two properties show some kind of stability of the set of Poisson point processes under some basic operation called superposition and thinning. Okay? You also need assumptions of independence in those two theorems. Finally, we are going to look at the conditioning property. So the conditioning property that I could find in any textbook said that if you look at a Poisson process and you assume that the process jumped exactly n times between time 0 and time t, then the position in time of those jumps are accurately described by n independent uniform random variables on the interval 0t. Now, it turns out that intuitively this result must also be true in higher dimension from the point of view of Poisson point processes, in which case the result would say that if you take a subset of, let's say, B of Rd, and you assume that there are n Poisson points in this subset, then the spatial distribution of those n Poisson points should be described globally by n independent uniform random variable on the set B. However, for some reason, I could not find any proof of this result anywhere in any textbook or even online, but I was able to write a proof myself, and so I'm going to show you the proof I found that basically extend the conditioning properly that is well known for Poisson processes turns out in fact to be also true for Poisson point processes. Okay, I'm sure people did it before. I don't know why the proof is not available anywhere. I could not find any. And so most likely this video is the first YouTube video that indeed gives you a complete proof of the conditioning properly, not just for Poisson processes, but more generally for Poisson point processes. So first, let's define those notions of Poisson point processes and Poisson processes, and I'm going also to show you that a Poisson process can indeed be viewed as a one-dimensional version of a Poisson point process. So here is a realization of what we call a Poisson point process. These are points like that we call Poisson points that are randomly distributed in space. Okay? And so the first question is, which type of mathematical object or stochastic process that consists of a collection of random variables should we use to indeed describe this type of process? Okay, so remember that so far the specific types of stochastic processes we saw are discrete time Markov chain and martingales. In this case, you have something that evolves in time, okay? And the index set of those processes are the set of natural numbers that corresponds to discrete time, the possible times of the process. In this case, at the opposite, we have something that does not evolve in time, but that is by nature spatial. And the question is, how can we use a stochastic process or collection of random variables to describe the spatial distribution of those points? Okay? And so clearly, if you assume that for any possible subsets of R2, in this case of Rd in general, a set like that, if for any possible such subset you know exactly the number of Poisson points in this subset, then you clearly have a full description of this picture here. Okay, and that's kind of the idea. To describe a Poisson point process, you need to define the process as basically a collection of random variables indexed by the set of all possible subsets of Rd that are going to count the number of Poisson points in each subset. So more precisely, if you call this subset here B, okay, I'm going to call n of B the number of points or Poisson points in this subset B, okay? N of B is a random variable, and the process that is going to indeed describe a Poisson point process is an example of counting process. That's basically something that I'm calling capital N like number of points, that is consists of the collection of all the possible random variable n of b for all b subsets of Rd. Okay? And so, like I mentioned before, now the index set is completely different from the index set for discrete Markov chain or martingales. Now the index set of the process consists of all the possible subsets of Rd. So remember that in chapter 4 of this playlist, I define a stochastic process as a collection of random variables that I call xi for little I in capital I. Okay? In discrete time, capital I consists of the natural numbers, all the positive integers. In continuous time, that would consist of the positive real numbers. In the case of a counting process, things become much more complicated. Now, the index set consists of all the possible subsets of Rd in general, R2 in the picture. Okay, so this is the type of object we need, but you see also that if the NB cannot be whatever, so that this is indeed a counting process that is consistent with the interpretation, number of points in the set B, we need some condition, some properties. For instance, we want n of the empty set to be equal to 0, okay? The empty set is empty, no Poisson point can live there, so n of the empty set should be equal to 0. Another condition we will need, for instance, is the fact that if A and B are two non-overlapping subsets of RD, disjoint subset of RD, then the number of points in the union should be equal to the number of points in A plus the number of points in B. Or things like monotonicity, if A is a subset of B, then the number of points in A should be less or equal than the number of points in B. It turns out that all those properties that are consistent with the fact that we indeed have a counting process can all be deduced from one axiom, and that's the fact that n must be sigma additive. Okay? So that's exactly the same definition as for a positive measure. Okay? I'm going to say that n is sigma additive if you take a collection of subsets of RD that I'm going to call Bj, assuming that those subsets are mutually exclusive, then the n of the union is the sum of n of Bj, meaning that the number of points in a union, a countable union of disjoint subsets, must be equal to the sum of the number of points in each of those subsets. Exactly like for a positive measure. And if you assume this condition, sigma additivity, you can easily, exactly like for a positive measure, prove, for instance, that the number of points in the empty set is 0. Monotonicity, if A is a subset of B, then the number of points in A is less or equal than the number of points in B. Set difference, if A is a subset of B, then the number of points in A but not in B, in B but not in A, is equal to the number of points in B minus the number of points in A. And inclusion-exclusion principle, which is true for any finite number of sets. I just take the result for only two sets. In the case where A and B may overlap, then the number of points in the union is equal to the number of points in A plus the number of points in B minus the number of points in the intersection. Okay? So these are the same properties as for a positive measure. So you can think of a counting process n as the same, more or less, as a positive measure. The main difference between the two objects is that a positive measure has value in R plus. Okay? All positive real number can be the actual value of the measure of a set, while in this case, in the case of a counting process, the range for n, or the possible values of n, it consists of the integers, okay? Because the number of points in a set is an integer, not a real number. Okay, so that's the type of object we need with this condition to be able to describe the distribution of points in space, and so to describe this type of feature. So now, to indeed have a Poisson point process, you need to impose a few more conditions, and in particular, one condition is going to involve the Poisson random variable. Okay? So, I remind you that the Poisson random variable with parameter alpha, okay? Poisson depends on one parameter, let's call it alpha. Poisson with parameter alpha is going to be equal to n with probability alpha to the power n divided by n factorial e to the minus alpha. It's important to have this definition in mind because I'm going to use this definition a lot at the end of this video to prove the main three properties of Poisson point processes, superposition, thinning, and conditioning. Okay? Then, using the Poisson distribution, you can define a Poisson point process that way. So a Poisson point process is going to be an example of counting process, the way I just described. Capital N equals to n of B for all B subsets of R, of RD, okay? And this is going to depend on one parameter, mu. Mu is going to basically measure the frequency of points, okay? And we call this parameter the intensity. To have a Poisson point process, you need two conditions. That's at least the definition I'm going to use through this video, but there is another equivalent definition I'm going to give you right after. So the first condition says that NB1, NB2 up to NBk must be independent random variables if the set B1, B2 up to Bk are mutually exclusive. So this condition says more or less that non-overlapping regions are independent, meaning that the number of points in non-overlapping region are independent random variables. Okay, so that's the first condition. The second condition, where the Poisson distribution appears, tells us that the number of points in any possible subset B of Rd, okay, is a random variable that is Poisson distributed with parameter mu times the Lebesgue measure of B. Okay, so that's where the Poisson distribution appears. So that's the definition I'm going to use in this video. Now, another equivalent definition is the following. It consists in thinking of a Poisson point process as a limit of what we call a Bernoulli process. Okay? And in this case, the conditions we need are the following three. The first one is the same as here. Non-overlapping regions are independent. Okay? The second one says that NB, which is a discrete random variable, and so characterized by a probability mass function. Okay, so the probability mass function in this case should only depend on B through its Lebesgue measure. Okay, so if you take two subsets A and B that have the same Lebesgue measure, then the number of points in A and the number of points in B must have the same distribution. The actual subset does not matter. What matters is the Lebesgue measure. Okay? And then third condition looks at the number of Poisson points in a very small subset. Okay? That's why we take lambda B going to 0. So if B is very, very small, okay, then the probability of one Poisson point in the set B should go to 0 as the Lebesgue measure goes to 0, but this is still proportional to the Lebesgue measure of B, and so the probability of one Poisson point in B should basically scale like lambda of B, and the proportionality constant is basically the intensity. Okay, so in any very small set, you will see one Poisson point with a probability that is roughly equal to mu lambda B. The second condition tells you that you do not have some kind of aggregation of points at the same place. It says that if your set B is very small, then the probability of strictly more than one Poisson point in this set is going to be negligible compared to the Lebesgue measure of the set B. Okay? So, it turns out that indeed those two definitions are equivalent. I'm going to use the first one through this video, but again, some authors prefer define a Poisson point process using the second definition. So I'm going to quickly explain why indeed they are equivalent. Clearly, the first one implies the second one. Okay? The first condition here is the same as here, so we don't have to take care of that. Here we only need to prove that the two conditions here are indeed satisfied, indeed follow from those two axioms. That's not difficult. Here you see clearly that point number 2 here says that the probability mass function only depends on the Lebesgue measure and not the actual set B. That's indeed the case here. If you assume that n of B is Poisson with parameter mu lambda B, indeed this distribution function only depends on B through its Lebesgue measure. So point 2 is clear. And to prove point 3, that's very easy. That's based on basic calculus. You can just write the probability that NB equals 1, probability that NB is strictly larger than 1, using the fact that n of B is Poisson with parameter mu lambda B, and using this expression for the probability mass function, and you will easily realize that indeed this is of the order of mu lambda b, and this is indeed negligible compared to lambda b. Okay, so proving that the second definition implies the first one is more difficult but also more interesting. Again, point 1 is the same, so we only need to prove point 2. And the idea to prove point 2 is just to say, let's take a subset B of Rd, and we can look at a partition of this set B into little n subsets that all have the same Lebesgue measure equal to lambda b over n. Okay? Then, because those subsets, they form a partition of B, they do not overlap. So the number of points in those subsets are independent random variables. Also, if n is very large, then lambda b over n is small. And so those properties are true. And you can say that in the limit, when n is very, very large, you are going to have a set B that is partitioned into n subsets that are all small, and each of them independently is going to have one Poisson point with this probability, lambda mu lambda b, but divided by n, okay? Because none subsets have Lebesgue measure lambda b over n, and by this second property, none of the other subsets is going to have more than 1 point. They are going to have 0 points. Okay? And so eventually, you can write the number of Poisson points in B using this construction as a binomial random variable with first parameter number of tries equal to n. That's the number of subsets in the partition. Okay? And second parameter, the success probability, that is going to count the number of such subsets that contain exactly one Poisson point. The success probability is going to be mu lambda b over n. Okay? So eventually the number of Poisson points, okay, in B is going to be binomial with first parameter n, second parameter mu lambda b over n. We know that this type of random variable, this binomial, when the number of tries is large but the success probability is small, is going to converge to a Poisson random variable with parameter, the product of the two parameters. So with parameter n times mu lambda b over n, that's exactly mu lambda b that we have here. And so that shows that indeed those conditions implies point 2 here. So the two definitions are indeed equivalent. Okay, so now let's look at Poisson process. So a Poisson process is a completely different type of object a priori, but in fact this is similar to a Poisson point process in one dimension. I'm going to explain that after, but first let's define the notion of Poisson process. A Poisson process is a process I'm going to call X that consists of collection of random variable xt, where now t is a real number, a positive real number. Okay? So in particular, that's, you can think of X as a continuous time process. Okay? And to have indeed a Poisson process, you need to assume that x0 equals 0, and the two main conditions are here. You need to have also independent increments. Okay? So if you write the condition, independent increments means that if you take 2k times t1, t2, t3 up to t2k in this order, okay? Then from those 2k terms, you can create k disjoint time intervals, okay? The time interval t1, t2, the time interval t3, t4, and so on, up to t2k minus 1, t2k. This here, xt2 minus xt1, looks at the value of the process at time t2 minus the value of the process at time t1. That's exactly the increment of the process across the time interval t1, t2. And then you look at all those random variables. So all those random variables, in fact, represent the increment in each of those disjoint time intervals. Then the first condition says that those random variables must be independent. Okay? So the first condition says more or less that if you look at non-overlapping intervals in time, then the number of increments in those disjoint intervals must be independent random variables. Okay? Then, the second condition says that the increments should also be Poisson distributed. And what this means is that now if you take only one interval, st, so I take s less than t, I'm looking now at the increment across the interval st, that's exactly the value of the process at time t minus the value of the process at time s, xt minus xs. This is Poisson distributed with parameter mu times t minus s. Okay? So you see that we have the same parameter mu that appears in both. In the case of Poisson point process, we typically call this parameter the intensity, while for a Poisson process, we call this parameter the rate. Okay? So, now it turns out that if you look at exactly like this random variable, you see that's Poisson. The Poisson random variable has range 0, 1, 2, 3, and so on. So this means that for all s less than t, the number of increments, or the increment, I should say, in the interval st is basically an integer. That's random, but that's still an integer, okay? And so from point number 2, and the condition that x0 equals 0, you can deduce that a Poisson process is in fact a continuous time process with state space n, the set of natural numbers. The process starts at 0, okay? And then by this property, it tells you basically that it's going to jump to state 1, and then state 2, and then state 3, and so on, okay? So you see here we have an object that is a continuous time process that starts at 0 and then jump to 1, 2, 3, and so on. While here we have a totally different type of object that consists of a static model with points scattered in space in 1, 2, 3 dimensions and so on. Okay? But it turns out that indeed you can think of a Poisson process as a particular case of Poisson point process in one dimension. Okay? So the idea is really to take d equals 1 in the definition of a Poisson point process. Now instead of having points that are distributed in 2 dimensions, like in the picture I showed you, or in general in d dimension, you are going to have points distributed on a line, okay? And kind of the idea to go from the a Poisson point process to a Poisson process is really to think that space in 1 dimension can be interpreted as time. Time is a one-dimensional thing in our mind, going in one direction. If space in the first definition is the real line, then you can indeed think of space as time. So that's kind of the first idea to show the connection. I'm going to take d equals 1 in this definition and then think of space as time. And so the location of points in space becomes the time of occurrences. Okay? So, now to see that indeed the two are related, notice that if I choose, again, d equals 1, and so b1, b2, bk become subsets of d, if I choose those subsets to be intervals, then the first condition is going to tell me that the number of Poisson points in disjoint intervals are independent random variables, okay? Because indeed, those sets are mutually exclusive. But if I assume that B1, B2 up to Bk are intervals that are mutually exclusive, then I get exactly this point 1 here. So you can think of the first condition in this definition as a particular case of this condition if you assume that d equals 1 and if you assume that those sets B are in fact intervals, in this case mutually exclusive intervals. Okay, that's exactly the same number of points. Okay, becomes here number of jumps, but if you think of number of points as number of jumps, then this is indeed a more general statement than that. This one is a particular case of this one. Okay, then we can also prove that this point 2 here in this definition implies that we have indeed Poisson increment, okay, if again you rethink of a Poisson point as the time of an occurrence or the time of a jump, okay, and for that just take B equals a subset of R that is an interval, let's say interval ST. Then if B is an interval ST, then from the point of view of a Poisson process, what we are looking at is the basically number of increments in the interval ST instead of number of points. But from the point of view of a Poisson point process, the number of points in this interval ST is going to be Poisson distributed with parameter mu times the Lebesgue measure of the interval ST. But the Lebesgue measure of an interval is just the length of this interval, and the length of the interval ST is just T minus S. And so if you take B equals ST there, you obtain that the number of points or Poisson points in the interval ST is Poisson distributed with parameter mu times T minus S. That's exactly what we have here. Okay? And so, in conclusion, if you think of D, if you fix D equals 1, you think of space as time. You reinterpret Poisson points as times of an occurrence or time of a jump for the Poisson process, then you have indeed taking those subsets as intervals in the first definition, you indeed obtain the second definition. And so this shows that indeed a Poisson point, a Poisson process is, I would say, not equal, but mathematically equivalent to a Poisson point process in one dimension with the same parameter. More precisely, using this analogy I explained, you think of a point, position of a point in space as the position of a jump in time. Eventually, you can prove that if X is a Poisson process with parameter mu, and if N is a Poisson point process with intensity mu, then the value of X at time t, xt, is exactly equal to the number of Poisson points in the interval 0t. That's the connection between the two. So clearly, when you have a Poisson point process n in one dimension, you can define a Poisson point, a Poisson process xt using this transformation, and vice versa. Okay, so you can also visualize this equation, and this becomes the following. You just take the real line, okay? Then you take points that are distributed on the real line according to a Poisson point process with intensity mu. And let's say that time 0 is here, and then at time 0 you are indeed, if you look at the number of points in the interval 0, 0, that's clearly 0, that's n of the empty set. If you increase t here, you are still at number of points in 0t equal to 0, but when you reach this point, suddenly the number of points in 0t becomes 1. If you keep increasing t, you are still at 1. At 1 now, you have, for t in this range, you are going to have that the number of points between 0t is equal to 2, and so on. And if you draw a picture showing you exactly the number of points in 0t, what you get is exactly this picture. And this is exactly a realization of the Poisson process X. So it's clear from this picture that if you have a realization of a Poisson point process with intensity mu in one dimension, you can easily, using this transformation, looking at number of points between 0t, you can easily obtain xt. Xt turns out to be a Poisson process with right mu, okay? At the opposite, if you have the process X, the Poisson process with right mu, just by looking at the time of the jumps and drawing at exactly those time a Poisson point on the real line, you obtain again from xt your process n here, that is the Poisson point process. So indeed, if you assume that d is equal to 1, there is an obvious connection between a Poisson point process with intensity mu and the Poisson process with rate mu. So now let's prove that the interarrival times in a Poisson process, meaning the times between consecutive jumps of the process, are indeed exponentially distributed. So to visualize the result, I'm back to this picture here. It's important to have those definitions in mind also, where here I show you the connection between end, Poisson point process in one dimension, and x, a Poisson process with the same parameter. And now we are interested in the time between those different jumps. I'm going to call those times T1, T2, T3, and so on. Okay? So you can think indeed as those are as interarrival times. The process xt here is equal to 0, then it jumps to 1, 2, 3, and so on. So these are the times between the jumps. You can also think of the Tj as the distance between consecutive points from the point of view of the Poisson point process. Okay? And the theorem we want to prove is the following. Those interarrival times, Tj, are independent exponential random variable with the same parameter mu. Okay, so that's the same mu as the rate of the Poisson process or the intensity of the Poisson point process. Okay, so notice that clearly if n or x are given, you can clearly find those times, again, interarrival times for the Poisson process or distance between consecutive points in the Poisson point process. At the opposite, if you have those times, you can clearly reconstruct the process n and x. So that's why it's interesting to learn more about those times, because through this picture you see that you have basically three types of objects that in fact are the same. Okay? Having a Poisson point process in one dimension, or a Poisson process, or a sequence of independent exponential random variables are basically the same thing. Okay, they are all three mathematically equivalent. When we have one of the three, you can reconstruct the other two. Okay, so how do we prove this result? The fact that the Tj are independent and identically distributed, at least, is an easy consequence of the two conditions we have here in the definition. So first, let's prove that the Tj are indeed independent. Okay, so let's look at, for instance, the process at this time. The fact that increments are independent tells us that the time to the next jump, okay, and the time since the last jump must be independent. So why is that? Well, independent increment tells you basically that the number of jumps in this joint region of time must be independent. And so everything that happened before that time and everything that's going to happen after that time must be independent. Okay, so that shows that T3 and T4 are independent. And of course, you can do that for any two of those interarrival times. And so that shows that indeed, independent increments implies that those random variables Tj must be independent. Now, the fact that they are also not exponential yet, but at least must have the same distribution follows from the fact that we have Poisson increment, or more generally, what we call stationary increment. Stationary increment means that for all s less than t, xt minus xs must be a random variable that only depends on t minus s. Okay, we don't need Poisson at this stage. So, indeed, you can just say that if we look at the time to the next jump, starting from time t, you look at the process at time t, you look at the time you have to wait until the next jump, then this increment of time should not depend on the time t you start with, okay? That's the definition of stationary increment, and so that shows indeed that the time starting from this time you have to wait until the next jump or the time starting from here, you have to wait for the next jump, must be by this second properly identically distributed. And so that shows that indeed the TJ are identically distributed. Okay, so conclusion, from the two conditions in the definition of a Poisson process, we can easily conclude that those times TJ are independent and identically distributed. Okay, that follows again from those two axioms. Okay, so then to conclude, we also need to prove that the TJ are exponential with parameter mu, and this is based on basically the connection between Poisson and exponential. We can prove that in some sense Poisson implies exponential. And so the idea to prove that is simple. You just say that because those times TJ are identically distributed, instead of looking at the distribution of TJ in general, it's enough to look at the distribution of T1. And if you look at the probability that T1 is larger than T, meaning that T is somewhere there, okay, that's if T is here, like at the level of my pencil, that shows the event that T1 is larger than T, then that means exactly that there are no Poisson points in the interval 0T. Okay? So that's how you get exponential from Poisson. You just say that the probability that T1 is larger than T is exactly the probability that the first jump is after time T. And so that's also the probability that there are no jumps of the process between time 0 and time T. Okay? And then the exponential random variable comes naturally from the expression of the probability mass function of the Poisson random variable. So more precisely, we can write the following. You just said that the probability that TJ is larger than T because we just proved that those random variables are identically distributed. That's the same as the probability that T1 is larger than T, which by the argument I showed you here is the same as the probability that xt is equal to 0. But we know that xt is the same because x0 equals 0 as xt minus x0, that's the number of jumps in the interval 0t, that's going to be Poisson distributed with parameter mu times t. And using, so that's probably that Poisson with parameter mu t is 0, and using this expression, you see that taking n equals 0, you get exactly alpha at the power 0, that's 1, 0 factorial, that's 1, e to the minus mu t in this case. Okay? And then, once you know this, you can easily get the distribution function of TJ, that's just the probability of the complement. Okay, so that's going to be 1 minus this expression. And to get the density function of TJ, you just look at the derivative of the distribution function, and then eventually you get the following. You can say that the density function of TJ, that I'm writing f sub TJ, is equal to the derivative of 1 minus the expression we just found. This is 1 minus indeed the distribution function. Distribution function is the probability that TJ is less or equal to T. If you look at the derivative of this expression with respect to T, you find mu e to the minus mu T. By definition, this is indeed the density function of the exponential random variable with right mu. And so in conclusion, not only the TJ are independent, you can also prove that the TJ are all exponential with the same parameter mu. So now let's prove that the exponential random variable is the only continuous random variable that is memoryless. And like I mentioned at the beginning of this video, this result is going to be extremely important in the next chapter that covers continuous time Markov chain, because it follows from the Markov property in continuous time that times between jumps in a continuous time Markov chain must be memoryless. And so the results we are going to prove now shows that those times also must be exponential. And so that's going to give us a way to construct a continuous time Markov chain using a collection of independent Poisson processes. So more precisely, we want to prove the following theorem. For all t random variable that is continuous, okay, exponential is the same or equivalent to memoryless. And memoryless means that for all t and s positive real numbers, the probability that capital T is larger than t plus s, given that t is larger than little t, is equal to the probability that capital T is larger than s. So before proving the result, let's look a little bit at this definition. That's kind of interesting. It tells you basically that a conditional probability on the left that depends on t and s is in fact equal to a probability that only depends on s. And so, in other words, that means that the conditional probability on the left, in fact, does not depend on t. Okay? And if you think of t as the time to the next jump in a Poisson process, for instance, you can think of this conditional probability as saying that given that the time since the last jump is at least equal to t, then the probability that we still have to wait s units of time does not depend on t. And so that shows that the time to the next jump does not depend on the time since the last jump. Okay, so that's one way to explain this idea of memoryless, not using an equation but using English. The time to the next jump in the future and the time since the last jump in the past are independent. If you think of t as a waiting time, okay, this means also, and that really underlines this idea of memoryless, that the time t you've waited so far does not matter. The time, the probability that you still have to wait s units of time does not depend on time t. So no matter how long you've waited, what you still have to wait did not change in distribution. Okay, so you can forget the past. The past does not affect the future. And so indeed, this shows that this random variable t is memoryless intuitively. That's the intuition behind the notion of memoryless. So now, how do we prove this result? Well, we have to prove two implications. Exponential implies memoryless is extremely easy to prove. The proof just goes like that. Let's assume that t is exponential. So in particular, there exists a mu positive such that t is exponential with parameter mu. I remind you, this means that the density function of t is equal to mu e to the minus t. But we saw in the previous slide that an equivalent definition of exponential is to say that the probability that capital T is more than t is equal to e to the minus mu t. If you just use this characterization, you see that this conditional probability here that you recognize on the left, by definition of conditional probability is equal to the probability of the intersection divided by the probability of this event. Now, s and t are both positive. So clearly, if t is larger than t plus s, then obviously t is going to be larger than t. So this implies that, so the intersection of those two events is only the event on the left. Okay? And from that, you can deduce that this conditional probability is just the probability that t is larger than t plus s divided by the probability that t is larger than t. Now, if you use this over characterization of the exponential random variable that we saw in the previous slide, you can say that this probability and this one are just equal to e to the minus mu t plus s divided by e to the minus mu t. Clearly, this simplifies and you just get e to the minus mu s. And using, again, the characterization, e to the minus mu s must be equal to the probability that t is larger than s. So we see that indeed, when t is exponential with some parameter mu, then this conditional probability that a priori depends on t and s in fact only depends on S. That's equal to the probability that T is larger than S. This shows indeed that T is memoryless. Okay? Now, to prove the converse, things become a little bit more tricky. What we are going to use is another characterization of the memoryless property that kind of appear in this calculation. You see that the fact that this conditional probability is equal to this ratio here is not true for T exponential. That's true for any random variable. Okay, that was just based on the fact that T plus S is clearly larger than little t. Okay, and so another way to define memoryless is just to say that T is memoryless if the probability that T is larger than T plus S is equal to the probability that T is larger than T times the probability that T is larger than S. Okay? And so we can just use this characterization to prove that memoryless implies exponential. More precisely, I'm going to define a function phi of t equals to the probability that T is larger than T, and the goal is going to be to prove that phi of t is of the form e to the minus mu t, but the assumption we can use that follows from memoryless is the fact that this expression, which is just phi of t plus s, is going to be equal to phi of t times phi of s. So more precisely, to prove the converse, I'm going to call phi of t this probability, okay? And then, like I just explained, T memoryless, meaning that this is equal to this times that, means exactly that for this function phi of t plus s is equal to phi of t times phi of s. So phi is a function that turns sum into product, okay? And the goal is to show that for all t real number, phi of t is equal to e to the minus mu t. That's going to show that indeed there exists mu such that t is exponential with parameter mu. Okay? And so the idea is to prove again that any such function that turns sum into product that is also continuous, and that's the case here, because we assume that the random variable t is continuous, so that makes this function continuous in little t. The goal is to prove that any continuous function that turns sum into product must be of exponential form. All right? So, step one, we need to somehow identify our parameter mu. Okay? To find mu, we just use the value of phi of 1, and that's how we fix the parameter mu. And then the goal after, once we have this mu, is to prove that phi of t is equal to e to the minus t. And the way we find mu is just by saying mu is equal to minus the natural log of phi of 1. Okay? So phi of 1, by definition, is the probability that t is larger than 1. That's a probability. In this case, that's going to be strictly between 0 and 1. So the log is going to be strictly between negative infinity and 0. And so minus the log is going to be strictly positive and finite. That's how we fix the parameter mu. That's how we find the parameter mu. You can find it from any of the values, you know, phi of t, but you have to fix one specific t. It makes sense to take t equals 1. Okay, so we find mu like this. Clearly, if you solve this for phi of 1, you find phi of 1 equals e to the minus mu. Okay? And so now, to complete the proof, the idea is, now that we have our mu, the goal is to prove that for any possible positive real number t, phi of t is going to be e to the minus mu t. That's going to show that indeed this random variable t must be exponential with parameter mu. Alright, so notice that we already have this result for t equals 1. Okay, from the definition of mu, we have that indeed phi of 1 is e to the minus mu, that's e to the minus mu times 1. Okay, so now the fact that any continuous function that satisfies or turns sum into product is of exponential form is a well-known result in real analysis. I'm going to show you the proof quickly. The proof is interesting. The idea is to first prove the result for the integers, and then deduce from that the result for all the rational numbers, and deduce from that the result for all real numbers. And in some way, the proof follows the construction of those sets. So to prove the result for natural number, integers, we are going to use induction. Induction is something we can do on the integers, not with rational numbers or real numbers. So step one will be to use induction. To prove step two, we are going to use the fact that any rational number can be written as an integer divided by another integer. So that's how you can construct the set of rational numbers from the set of integers. Okay? And for step three, going to all the real numbers, we are again going to use some type of construction of R. Have in mind, remember that the set of rational numbers is not complete, meaning that there exist Cauchy sequences of rational numbers that do not converge, and that's the role of R is to avoid this lack of completeness. And so, in particular, any real number, by definition, can be written as the limit of a Cauchy sequence of rational number. Okay? So using this ID and the fact that phi is continuous, we'll be able to deduce the result for all t in R. That's the idea of the proof. That's a classic in real analysis. So more precisely, step one consists of the following. I want to prove that phi of n is equal to e to the minus mu n for all n integers. Now, the only thing I know is this: you can turn sum into product. And so what you do is just say n is just equal to n minus 1 plus 1. And so from this equation in blue, you can just say phi of n is also the same as phi of n minus 1 times phi of 1. And you repeat that n times total. And in fact, after you can write that this is phi of n minus 2 times phi of 1 times phi of 1, and so on. And eventually you get that this is just the product of phi of 1 n times, that's phi of 1 at the power n. But because phi of 1 is e to the minus mu, eventually you get that this is e to the minus mu at the power n, that's indeed e to the minus mu n. So that shows the result here we want to prove, but for all integers. Now, to go to the set of rational numbers, like I told you, we are going to say any rational number R can be written as P over Q, where P and Q are integers. Okay, so that's what we are doing here. And then, because we only know so far the result for integer, instead of looking at e to the minus mu R, I'm going to look at e to the minus mu p. P is an integer. And by the previous step, we know that e to the minus mu p is equal to phi of p. That's what we just proved. Okay? Then, look at this expression. P can be written as q times r. R is a rational number, but q is again an integer. So again, you can write p equals qr, but qr is equal to r plus r plus r plus r q times. And repeating the same idea as in the previous steps, eventually you get that phi of p is phi of qr, which is phi of r at the power q. Okay? And then taking the power 1 over q on both sides, here and here, you get exactly that phi of r is equal to this quantity at the power 1 over q. That's exactly e to the minus mu p over q, which is e to the minus mu r. So that shows indeed that this is true for all rational numbers. Okay? Then, last step, we know the result for rational number. We want to deduce that it's also true for real numbers. Now I'm going to take a very general positive real number, t, And again, by definition of R, T can be written as a sequence of rational number that I'm going to call Rn. And because phi clearly is continuous, T is a continuous random variable, so this function here as a function of little t is continuous, we can say that phi of the limit of the Rn is equal to the limit of phi of Rn. And that's going to give us the result. So more precisely, now I'm taking t positive real numbers, then a sequence Rn of rational number converging to t. Then phi of t is going to be equal to phi of the limit of the Rn. Okay? By definition, the limit is equal to t. Then I can extract the limit here because phi is a continuous function. It's continuous everywhere, so in particular that's continuous at point t. So we can extract the limit, and now we end up with a quantity here, phi of Rn, that we can express explicitly from the previous step. Rn is a rational number, so phi of Rn is e to the minus mu Rn that we have here, and obviously this function is continuous, so you can put back the limit inside and you get that it's e to the minus mu t. Alright, and so we were able to prove indeed that if t is memoryless, meaning that phi of t satisfies this condition, turns sum into product, and also because t is continuous, is a continuous random variable, this function also is continuous. Using those ingredients, you can deduce that indeed there exists mu defined here, such that for all t, phi of t is equal to e to the minus mu t. And this is, like we saw before, a characterization of exponential. And so you can conclude that, so probably that t is larger than t is this for all t, and so in particular t is indeed the exponential random variable with parameter mu. So now let's look at the three main properties of Poisson point processes and Poisson processes, starting with the superposition property. So, like I told you, the superposition property is easier to visualize using a Poisson point process instead of Poisson processes, so that's this point of view that I'm going to use to prove the result. And here is a picture of just the property for only two independent Poisson point processes, but of course the result is true for any finite number of such processes. So more precisely, I'm going to take a bunch of points, Poisson points with intensity mu1. I'm going to visualize the result assuming that those points are blue, and same, I'm going to take a collection of white points that are distributed according to a Poisson point process with intensity mu2. It's important also to assume that those two processes are independent. Okay? Then, if I look at the superposition of all of them, okay, I obtain basically this picture with blue and red, and it turns out that what we see here is exactly a Poisson point process with intensity the sum mu1 plus mu2. Okay, those numbers also correspond to a second part of the superposition property that says that if you take a given point in this picture, without looking at the color, let's say, then this point is going to be blue with probability mu1 over mu1 plus mu2, or red with probability mu2 divided by mu1 plus mu2. So this tells you that if you look at superposition of any finite number of independent Poisson point processes, then the result is again a Poisson point process with intensity the sum, and in this new process, each point is going to be independently with color I with probability mu I divided by mu1 plus mu2 and so on. And so that tells you that the intensity of the original process also measures the frequency of each of the color in the final process. Okay, so that's a picture explaining the superposition property. Now we have a like more rigorous statement saying that assume that points with color I that can be 1, 2, 3 up to capital K, let's say, are distributed according to independent Poisson point processes that I'm going to call Ni, with intensity mu I. And let N be the superposition of all the points. So, in particular, the way you obtain this process from the point of view of counting process is by saying that for all subset B of Rd, N of B is going to be equal to N1 of B plus N2 of B up to Nk of B. You look at the sum of all the points in each set. Then, two conclusions. The first one says that N, in fact, is a Poisson point process with intensity the sum, mu1 plus mu2 up to mu k. And the second part of the superposition property tells you that each point, each Poisson point in N has color I with probability mu I divided by the sum mu1 plus mu2 up to mu k, which we call mu. Okay? So, that's the superposition property. Here you have again a visualization, superposition of all points. If I color all of them black, then what I see here without the colors is exactly a Poisson point process with parameter mu1 plus mu2. So, to prove point number 1, there are two things we need to prove. We need to go back to the definition of a Poisson point process. Remember that must satisfy two conditions. First, a condition of independence, saying that non-overlapping region, like number of points in non-overlapping region should be independent. Okay, that's the first thing we need to prove. And to prove one, we also need to prove that the number of Poisson points from the point of view of the process N in a set B is going to be Poisson distributed with parameter the intensity, which is the sum of the mu I, this mu, times the Lebesgue measure of B. Okay, so that's the first two things we need to prove, and then we can also prove number 2 after. So, first, it turns out that, if you think about it, it's enough to prove the result only for two colors, and so I can use those pictures with the color blue and red, and then you can deduce the result in general for any K by induction. The idea is simple. If you have K processes like that are independent, you can just look at the superposition of the first two, use the result for K equals 2, and say that the superposition is again a Poisson point process with parameter intensity mu1 plus mu2. And then you can superpose this one with the third one, but the superposition of the first two and the third one are independent, and so you can again apply the result for K equals 2 to deduce that it's true for K equals 3 and so on. Okay? So it's enough to prove the result for K equals 2. Okay? And to prove the first axiom of a Poisson point process, I'm going to take K disjoint non-overlapping subsets of Rd. I'm going to call them B1, B2 up to Bk, and N1, N2 that are independent. That's the assumption of the theorem. And what we need to prove is basically that N of B1 up to N of Bk that are equal to N1 of B1 plus N2 of B1 up to N1 of B1, Bk plus N2 of Bk are independent. Okay, so things are easy. The idea is just to notice that those random variables, so you have 2k of them. 2k comes from two colors times k subsets. Ni of bj for I equals 1 and 2 and j equals 1 up to k are independent. So why is it the case? The fact that N1, B1, N1, B2 up to N1, Bk are independent comes from the definition of a Poisson point process, comes from the fact that N1 is a Poisson point process. You have the same property for N2, N2B1, N2B2 up to N2Bk are going to be independent. Okay? But we also assume that N1 and N2 are independent. That's in the statement of the theorem. You have independent Poisson point processes, and so that shows not only that the set of K random variable n1 b1 up to n1 bk are independent and n2 b1 up to n2 bk are independent, that also shows that n1 b1 and n2 b1 must be independent, and so on. So eventually you end up with a set of 2k random variables that are independent. And to reconstruct the process n, what you do is, in the superposition, you look at a number of points of bj equal to number of blue points plus number of red points, but you see that those random variables are obtained by pairing basically those 2k ones into k pairs that are kind of disjoint, okay? And so eventually you obtain indeed a set of k random variables that are independent, okay? So conclusion, if you take k disjoint subsets of Rd, then b1 up to bk, then nb1, nb2 up to nbk are independent. That's the first condition in the definition of a Poisson point process. All right, so now 1b, that's the second thing we need to show to prove the first statement, is the fact that now for all b subset of Rd, nb is going to be Poisson distributed with the correct parameter. The parameter should be mu, which in this case is just mu1 plus mu2 times the Lebesgue measure of b. All right, so for that, to simplify a little bit the notation, I'm going to take b subset of Rd. I'm going to call alpha I the quantity mu I times lambda b. From the assumption of the theorem, we know that ni, in general, ni of b is going to be Poisson distributed with this parameter, so alpha I, and also I'm going to call alpha the sum alpha 1 plus alpha 2, okay? And then to prove the theorem, so the goal is just to use that NIB is Poisson with parameter alpha I, and use the fact that they are independent. And another key result we are going to use is the binomial theorem. But if you think about it, the only thing we need to prove is that n of b is Poisson with parameter alpha. And so the goal is to prove that the sum of two Poisson random variables that are independent with parameter alpha 1 and alpha 2 is again Poisson distributed with parameter the sum. So behind the superposition property, one key result we are going to use, which is a well-known result in probability theory, is the fact that the sum of two Poisson random variables is equal to Poisson with parameter the sum if those two random variables are independent. Okay, so that's a well-known result, but I'm going to prove this again. The idea is to start with looking at the probability that NB is equal to N. We want to prove that NB is Poisson with parameter alpha, so we need to prove that this probability is equal to alpha to the power n over n factorial times e to the minus alpha. So we do not know NB yet, but we know N1B and N2B. We know that N of B is equal to the sum of the two, and so clearly the even that N of B is equal to N is exactly the even that N1B is 0 and N2B is N, or 1 N minus 1, or 2 N minus 2 up to N 0. That's all the possibilities, and that's why I have the sum here, okay? So I have basically, I can rewrite this as this event as a union of n events that each consist of the intersection of two events. But because those events are mutually exclusive, you can write that as a sum for n equals 0 to n. And I'm using one more property here, that's independence, that I use here for this equation. I just said that the probability that n1b is m and n2b is n minus b is just the product of the probabilities. So I can turn the probability of the intersection into product of the probabilities by using independence. Now, we are done with the probability part, I would say. The rest of the proof is just basic calculation. Clearly, we don't know n of b, but we know n1 of b and n2 of b. And we know that they are Poisson distributed with parameter alpha 1, alpha 2. So I can compute those two probabilities explicitly, and that's going to give us this expression, okay? It's just the probability that a Poisson with parameter alpha 1 equals m, the probability that a Poisson with parameter alpha 2 equals n minus m, okay? And then, if you look at this expression, you see that the e to the minus alpha 1, e to the minus alpha 2 do not depend on m. The sum is over m, so I can put those two terms outside. That's going to give me an e to the minus alpha 1 plus alpha 2, which is exactly e to the minus alpha. That's a term we need. Notice also that you have an m factorial n minus m factorial here, but m plus n minus m is equal to n. And n is not the parameter in the sum is over m. And so when we see that, we kind of want to multiply inside the sum by some n factorial, so that eventually the n factorial divided by m factorial n minus m factorial gives you an n choose m. Okay? So that's what I'm going to do. I'm going to extract the exponential, multiply inside the sum with an n factorial, to have an n choose m, but of course I need to divide also by n factorial outside. And so eventually we get this expression. The exponential now are here, divided by n factorial, and then we have the sum of n choose m, alpha 1 at the power m, alpha 2 at the power n minus m. Now, by the binomial theorem, we see that this quantity is just alpha 1 plus alpha 2 at the power n. Okay, and recalling also that, again, here alpha 1 plus alpha 2 is equal to alpha, we end up with alpha at the power n, that's this sum, divided by this n factorial, times e to the minus alpha, that's this term here. Okay, and so eventually, we conclude that for any subset B of Rd, n of B is Poisson with parameter alpha, that's this expression, but recalling the definition of alpha and alpha 1, alpha 2, you can replace alpha by this expression that tells you n of B is, for any subset B of Rd, Poisson distributed with parameter mu1 plus mu2 times lambda B. That indeed shows, with the previous property we proved, that n is a Poisson point process with parameter mu1 plus mu2. All right. So that shows the first part of the superposition property. For the second part, what I'm going to do is look at a conditional probability. I'm going to look at the probability of, let's say, a blue point in a set B, given that we have only one point in this set. And the goal is to prove that this is indeed equal to the intensity of blue divided by the sum of the intensities. All right, so more precisely, to prove two, again, to simplify the notation, I'm going to take B subset of Rd. I'm taking the same alpha I alpha, and I'm going to, I recall that what we know by assumption is NIB is Poisson with parameter alpha I, and what we just proved is that n of B is Poisson with parameter alpha. Then, from that, we can compute this conditional probability, the probability that a given point has color I in general, let's fix I equals 1 for instance, is going to be the probability that n1b equals 1 given that n of b equals 1. So this says that if we take a set B that has only one Poisson point, what is the probability that this set, this point has color 1? Okay? And we want to prove, to get this, that this is indeed equal to mu1 over mu1 plus mu2. And so, for that, you just, again, look at the definition of conditional probability. That's going to be probability of the intersection divided by the probability that n of b equals 1. But the intersection is exactly the probability of one point with color 1, and so 0 point of the other colors, okay, of color 2. And so eventually you obtain this. You obtain that this conditional probability is exactly the probability of 1 point with color 1, 0 point with color 2, divided by the probability of 1 point total. Now, we know that N1, B, and 2B are independent by assumption, so I can write the probability of this intersection as a product of probabilities. And we know that N1, N2, N are Poisson distributed with parameter alpha 1, alpha 2, and alpha that's written here. I can just replace this to get another expression. So yeah, first I'm doing independence, and then you can just replace by the expression of the probability mass function for Poisson, and you get this product here. This is the probability that a Poisson with parameter alpha 1 is equal to 1, probability that a Poisson with parameter alpha 2 is equal to 0, probability that a Poisson with parameter the sum alpha is equal to 1. And you see that in the numerator you have e to the minus alpha 1 plus alpha 2, that's just e to the minus alpha. This simplifies with this one, and then eventually we end up with alpha 1 over alpha 2. Okay? No, alpha 1 over alpha, sorry. But alpha is alpha 1 plus alpha 2, and so eventually you end up with the correct result. You have alpha 1 over alpha, but if you recall the definition of the alpha I, that just gives you a mu1 lambda b divided by mu times lambda b. This simplifies, the Lebesgue measure of b disappears, and eventually you get indeed mu1 over mu. Okay, so that shows the second part of the superposition property. All right, so you see I formulate the result for Poisson point processes because we have this nice visualization, but obviously we know that a Poisson process is a particular case of Poisson point processes in one dimension, so somehow this result should also be true for Poisson processes. And indeed that's the case, except that even if we still call this result the superposition property, the statement does not look at superposition of Poisson processes. This doesn't mean anything. You can look at superposition of points, but not really superposition of processes. But clearly, if you look at the connection between Poisson point processes and Poisson processes, this kind of tells you that the number of jumps of the process, of the Poisson process in a given time interval corresponds to the number of points in the Poisson point process. Now, if you look at superposition of points, then you are going to looking at the total number of points, add all the points, okay? Number of points in a time interval is going to be number of blue plus number of red. And so this tells you that because xt, your Poisson process at time t is equal to n of the interval 0t, number of Poisson points in the interval 0t, this tells you that superposing points of Poisson point processes is the same as looking at the sum of Poisson processes. And so, in particular, you can reformulate this result, saying that now if you have k independent Poisson processes with weight mu1, mu2 up to mu k, then the sum of them is going to be again a Poisson process with weight mu equal to the sum. Okay? So superposition for Poisson point processes is the same as sum or addition for Poisson processes. Now there is a third version of the superposition property, but for the exponential distribution. And you can, so there is a way to prove this result directly using integrals and so on, but it makes more sense to use the connection between exponential and Poisson. And remember that the exponential random variable appears if you look at the inter-arrival times, or the distance between consecutive points. Now, if you think of the distance to the next point, okay, if you have red and blue points, it's clear that the distance to the next point of any color is exactly the minimum of the distance to the next blue point and the minimum of the minimum of the distance to the next blue point and the distance to the next red point. Okay? So this tells you that we must have a version of this result for the exponential distribution. But instead of looking at superposition or sum, we look at the minimum of those exponential. Okay? And so, more precisely, we have the following theorem that is kind of equivalent to this one through the connection between exponential and Poisson, or Poisson point processes in one dimension, which says that if you call Ti exponential random variable with parameter mu I, and you assume that those random variables Ti are independent, then tau, which is the minimum of the tau I, tau 1, tau 2 up to tau k, is going to be again exponential with parameter of the sum. So you see that the fact that you add the intensity here becomes adding the parameters of those exponential there. And same for the second part, you can also prove that the probability that tau is equal to tau I, okay, meaning that tau I is the minimum of all of them, is going to be equal to mu I divided by mu, same result as here. All right, so like I told you, you can prove this result just computing integrals. Okay, you can just write the density function of exponential, use that because they are independent, the joint density function is just the product, compute some multiple integrals, and then you can prove this result. Instead of proving this result that way, there is an easier way to prove it, now that we know that the result is true for Poisson point processes and Poisson process, and also because we know that there is indeed a connection between Poisson processes and exponential. And so the idea is going to be to think of tau I not as just an exponential random variable with parameter mu I, but as the position of the first point in a Poisson point process with intensity mu I, or we can also think of tau I as the time of the first jump in a Poisson process with weight mu I. So more precisely, the way you can prove this result using only a picture and using this version of the superposition properly and the connection between Poisson and exponential is as follows. So you just draw a picture like that. I'm going to use again the point of view of Poisson point processes. That's easier to visualize. I'm taking a bunch of blue points on the real line. They are distributed according to a one-dimensional Poisson point process with parameter mu1. Same for white points that are now distributed according to a Poisson point process with intensity mu2. All right. Then, what this result says, okay, is that if I take the superposition of all the points on the same line, blue and red, then I end up with points that are distributed according to a Poisson point process with parameter of the sum mu1 plus mu2, which we call mu. Okay? Now, if you think of tau1 that must be exponential with parameter mu1, tau1 in the picture can be read here. The position of this point is exponential with parameter mu1. That's what we proved before. Okay? And so you can think of tau1 as the position of this point, or the time of this jump from the point of view of Poisson process. And you can think of tau2 as the position of this point. But then, this means that the position of this point here should be, by definition, the minimum of the two. That's exactly tau. Okay? And so eventually you can complete the picture like this. You think of tau1 and tau2 as position of the first blue point and first white point. Okay? And then tau appears here. That's the minimum of the two. But from this property, we know that those points are distributed according to a Poisson point process with parameter mu. And so this means in particular that the distance between consecutive points, or also the distance between 0 and this first point here, should be exponential with parameter mu. So that shows through this property that indeed tau is exponential with parameter mu. Okay, so the picture shows red before blue. You could have blue before red, in which case the first point that appears here is not red but blue, but in any case, tau is always the position of the first point, and the position of the first point by this version of the superposition property should be exponential with parameter mu. Alright, so now you can also look at the probability here that tau equals tau 1 equals tau I. In the picture, in this particular case, tau equals tau 2, okay? And then indeed, the probability that tau equals tau 2, if you use, again, this version of the superposition property, tells you that, that each point in n has color 2, red is 2 in our case, with probability mu2 divided by mu, okay? And so that shows that the probability that we indeed see red here by this second conclusion here should be mu2 divided by mu. In general, that's going to be mu I divided by mu. That's the probability that tau is equal to tau I. And so that gives you indeed this over condition here, second part of the superposition property, but for the exponential random variable, the probability that the minimum of those exponential is equal to the ith one is the rate of the ith of those exponential divided by the sum of the rates. Now let's look at the thinning property, which, like I told you at the beginning of this video, can be viewed as some kind of converse of the superposition property. And I'm going to again use the point of view of Poisson processes to visualize the property. And so we start with a Poisson point process with a given intensity mu. And this time, instead of superposing points, I'm going to extract points with given probabilities independently of each other. And so more precisely, what we can do from this picture is decide, for instance, to color each of those points independently, blue with probability P1 and red with probability P2. Okay? In those pictures, I assume that P1 plus P2 is equal to 1, so that each point indeed ends up to be blue or red. And if you look at the result, you have a set of blue points, set of red points. It turns out that this is again a Poisson point process, but this time with intensity mu P1, while this one, of course, by symmetry, is going to be a Poisson point process with parameter mu P2. So to summarize superposition and thinning property that you see both in this slide, basically those two properties tell you that if you have two independent Poisson point processes, the superposition is again a Poisson point process with intensity the sum. At the opposite, if you start with only one Poisson point process and you color points independently with different color, let's say color I with probability Pi, then the resulting set of points with color I is going to be again a Poisson point process, but this time the parameter is reduced by this probability Pi. Alright, so more precisely, we can state the result that way. Paint each point of a Poisson point process that I'm going to call n with intensity mu independently. The word independently here is important. Color I with probability Pi. Then if you call Ni the set of points with color I, you obtain a Poisson point process with intensity mu Pi. So the original intensity mu, but reduced by the factor Pi. That is, of course, less than 1. Less or equal to 1, that's a probability. Alright, so to prove the result, again, exactly like before, we need to prove two properties. The fact that if you take k subsets of Rd, ni b1, ni b2 up to ni bk are independent, number of points in non-overlapping region are independent. I'm going to skip this part. That's kind of obvious in this case. That was already obvious for the superposition properly. Instead, I'm going to focus on the second part of the definition of a Poisson point process. And what we need to do is prove that for any subset B of Rd, NIB is going to be Poisson distributed with parameter mu pi times the Lebesgue measure of B. Okay, so more precisely, to prove this result and simplify a little bit the notation, I'm going to take subset B of Rd. I'm going to, again, like before, call alpha this product mu times lambda B. We know that from those definitions, we know that n of B is going to be Poisson with parameter alpha. Okay? Then the idea of the proof is, the key step of the proof is this. Using independence, you can prove that the probability that NIB equals M given NB equals N is equal to the probability that a binomial NPI is equal to M. All right. So why is it the case? Well, that's the case because this conditioning here tells you that in the set B you have a total of n Poisson points, and you know by assumption that you are going to color each of those Poisson points independently. This is important. Independently color I with probability pi. So you can think of those n Poisson points as n trials, where for each point you have the opportunity to have one point with color I, and each time you succeed in coloring your point color I with probability pi. Okay? And so this tells you exactly that the number of points with color I is exactly going to be the number of successes, each happening with probability pi in a set of n tries. That's exactly the definition of the binomial. Okay, and so indeed the number of points with color I, given that you have n points total, is going to be binomial with parameter n pi. Okay, so that's the key step of the proof. That's kind of the main part, the main probability part. Next step is to compute the probability that NIB is equal to n, let's say, or m, but by conditioning on n of B, okay? And then that's just some calculation. So more precisely, next, conditioning on NB, exactly like we did here, we can say that the probability that NIB is equal to m, so probability of exactly m points with color I in the set B, is equal to the sum of probabilities of the same event, but given that n of B is equal to n times the probability that n of B is equal to n. I'm just conditioning on NB. We need a partition, and the partition I'm using is n of B equals m, or m plus 1, or m plus 2, and so on. Notice that here we can indeed take the sum starting from n equals m, because clearly if n is strictly less than m, then this conditional probability is 0. Okay? If you have less than n Poisson point total, you definitely cannot have more points with a given color. Okay? So that's why you can start from n equals m. Okay? So then the next step is simple. We know that this conditional probability is exactly this one. That's what we just explained. We know that n of B, by definition of a Poisson point process, is going to be Poisson distributed with parameter alpha. And so I can compute explicitly this probability and this one, and I obtain the following expression. Okay? That just sum for n equals m to infinity of n choose m pi at the power m 1 minus pi at the power n minus m. That's exactly this quantity here is exactly the probability that a binomial n pi is equal to m. And this one, alpha at the power n over n factorial e to the minus alpha, it's exactly the probability that a Poisson random variable with parameter alpha, that's this one, is equal to n. All right. So now, what can we do with this expression? Well, you see that the sum is over n. So I can move outside the sum everything that does not depend on n. And so in particular, I can move the pi at the power m outside the sum. I can move also the e to the minus alpha outside the sum. Notice also that we have an n choose m, but multiply by like a 1 over n factorial. There is an n factorial that appears in the numerator for this n choose m. I'm going to also simplify this expression. Eventually, the product this times 1 over n factorial is just 1 over m factorial times n minus m factorial. I'm also going to move the m factorial outside the sum. Okay? One more thing I'm going to do, which is not obvious at this stage, but that's going to appear after that. A natural thing to do is I'm going to split this alpha at the power n into an alpha at the power n minus m times alpha at the power m and put the alpha at the power m outside. If you do all this, you end up with this expression. Okay? So I have my alpha at the power n that becomes an alpha at the power m outside times alpha at the power n minus m inside. Then pi at the power m goes out, n factorial that you have in the denominator here goes out. You end up with sum of alpha at the power n minus m times 1 minus pi at the power n minus m divided by n minus m factorial. Okay? So now you see that this sum here, in fact, depends on not really n, but n minus m. Okay? You have power n minus m and n minus m factorial, but the sum starts from n equals m. When n equals m, obviously n minus m equals 0. So I can rewrite this sum just saying that this is the sum for n equals 0 to infinity of alpha 1 minus pi at the power n divided by n factorial. But we know that the infinite sum starting from n equals 0 of xn divided by n factorial is exactly exponential x. Okay? So this tells us that this sum here is in fact just equal to exponential alpha times 1 minus pi. Okay? So that's the next step here. We can just say that this sum is exponential alpha 1 minus pi. You see that you have a simplification when you collapse those two exponential. You have e to the minus alpha plus alpha minus alpha pi, that's just e to the minus alpha pi. Okay, and so if you recap, eventually you see that for all possible integer m, the probability of m Poisson points with color I in the set B is this expression. This means that NIB is exactly the Poisson random variable with parameter alpha pi. Now, remember that alpha is equal to mu times lambda b, and so that shows you that Ni is indeed the Poisson point process, okay, with parameter mu times pi. So that's the conclusion of this slide. Eventually, you conclude that NIB is Poisson with parameter alpha pi, but because alpha pi is mu pi lambda b, and because this is true for any subset B of Rd, we deduce that Ni is indeed the Poisson point process with intensity mu times pi. To conclude this video, let's look at the conditioning property for Poisson point processes. So, like I told you at the beginning of this video, this property is well known for Poisson processes. You can find it in a number of textbooks or even online. However, even if it seems that the property should also be true in higher dimension for Poisson point processes, I could not find the proof anywhere in textbooks or online, and so I'm going to show you the proof I came up with. So before stating the result in a higher dimension for Poisson point processes, maybe I should start telling you about the conditioning property that you can find in textbooks about Poisson processes. So this property tells you that if you have a Poisson process, the rate of this process does not really matter. In fact, given that xt is equal to n, meaning that you had n jumps of the process between term 0 and term t, then the position of those jumps in the interval 0t is in fact described by a collection of n independent uniform random variables on the interval 0t, after, of course, reordering. Now, it turns out that the result should be true in higher dimension, okay? And the proof for Poisson processes, in fact, relies on the connection between Poisson and exponential, and is a little bit messy, involves calculation using the density function of the exponential random variable. Now, when thinking of extending this result to higher dimension, of course, I could not use anymore the connection between Poisson and exponential. The exponential does not appear anymore in higher dimension, and so I had to come up with new ideas, and the proof I'm going to show you is, I would say, more theoretical than the one for Poisson processes, but it's also, I would say, more elegant because it does not use any specific calculation. The proof is much less messy. Okay, so let's see how we can indeed extend this conditioning property for Poisson processes, but to higher dimension. And so the statement becomes like that. I'm going to fix not an interval 0t anymore, but a very general subset B of Rd, okay? I again have in the background capital N, that's a Poisson point process with intensity mu, and I'm going to assume that n of b is equal to little n, meaning that there are n Poisson points of the process n in the subset B. Then I'm going to call those points P1, P2 up to Pn. These are the Poisson points in B. Those numbers here, I mean those values, in fact, here are vectors now. They are not real numbers, we are in higher dimension, they are elements of Rd. Okay? Then I'm also going to take an independent uniform random variable on the set B that I'm going to call U1, U2 up to Un. Then the theorem, like the extension of the known theorem but to higher dimension, says basically that the set U1, U2 up to Un is equal in distribution to the set P1, P2, Pn. So this shows that exactly like the well-known result, that the position of the Poisson point is indeed described by a collection of n independent uniform random variable. Notice that, but the result again was known in one dimension, now that's true in higher dimension. So notice that in the statement here, I'm not taking a vector, okay? I have braces here, and so by that I mean that globally, those n uniform all together collectively are going to have the same spatial distribution as those n Poisson points, okay? This statement does not mean that U1 is equal to P1 in distribution. It just means that this set altogether is equal in distribution to this set. All right. So, before I prove the theorem, I probably need to explain a little bit what we mean by uniform on the set B. Okay? I'm sure you know the uniform random variable on an interval, but now we are in higher dimension. Well, this is easy to define. You just say that uniform B is the random variable, the continuous random variable that is going to have density 0 outside the set B because we don't want our point to be outside B, and constant on the set B. so that the integral in higher dimension is indeed equal to 1, you need to impose that the common value of the density function on the set B to be equal to 1 over the Lebesgue measure of B. So that's what I mean by uniform. And another way to think of those uniform order variables, and that's an aspect that we are going to use in the proof, is the following. Take a subset A of B, then the probability that one of them, let's say U1, belongs to the set A is exactly going to be equal to the Lebesgue measure of A divided by the Lebesgue measure of B. That's what we mean by uniform. You can indeed prove that using the density function I just described. The probability that U1 is in A is going to be equal to the integral on the set A of the density function, 1 over lambda B, d lambda, that gives you exactly the Lebesgue measure of A divided by the Lebesgue measure of B. Okay, so that's what I mean here. Then, to prove the result, so first, we are going to notice that if indeed A is a subset of B, then the Lebesgue measure of the set B, but without A, so what we have around here, is going to be equal to the Lebesgue measure of B minus the Lebesgue measure of A. I'm going to call little b the Lebesgue measure of B and little a the Lebesgue measure of A to simplify the notation after. All right, so that's a key property we are going to use after. That's a well-known property. Then, to prove the result, what I'm going to do is basically show that this set of endpoints and this set of endpoints are in fact equal in distribution from the point of view of, again, counting process. Okay? And so, to prove that the spatial distribution of those two sets are equal in distribution, the only thing we need to do, okay, is prove that for any possible subset A of B, the number of those uniforms that are in A and the number of Poisson points that are in A are two random variables that are equal in distribution. Okay? So that's the goal. And so I'm going to start by looking at basically the probability that the cardinal of P is the set here, intersection A, is equal to M. Okay? M can be any number between 0 and n. We know that we have n Poisson point total here and n uniform also. And so the number of Poisson point or uniform in A can be any m between 0 and n. All right. So I'm looking at the probability that the cardinal is equal to m. That's exactly the probability that of those n Poisson points, exactly m of them are in this set A. All right, so to compute this probability, remember that this is true. This equation in distribution is true on this event, so we need to condition on this event. I'm going to just say that the number of Poisson points in A here is exactly equal to n of A. Okay, so we look at the probability that n of A is equal to m, but given that n of B is equal to n, that's our conditioning here. Okay, and then to compute this conditional probability, exactly like we did before, I'm going to use the definition that's probability of intersection divided by the probability that n of B equals n. But if you look at the intersection, you see that this is exactly the event that you have m points in A, n points total. So that's exactly the event that you have m points in A and n minus m points in B, but not in A. And so we can use this property here. So indeed, next step, you can write that this conditional probability is probability of m points in A times the probability of n minus m points that are in B but not in A, divided by the probability that nb is equal to n. Now, notice that in this equation, to get this equation, I used independence. Okay? And so how do we use independence? Well, this appears in the fact that the set A and the complement of A in B, which is B without A, those two sets here are mutually exclusive, they are disjoint, and so by definition of a Poisson point process, the number of points Poisson point in A and the number of Poisson point in B but not A must be two independent random variables. Okay, so we know that this one is Poisson with parameter mu times the Lebesgue measure of A, which is little a, so that's Poisson with parameter mu A. This one, by this property, is Poisson with parameter mu times B minus A. Okay, this one is Poisson with parameter mu times B. Okay, and clearly this one and this one are independent, so I can write the probability of intersection as product of the probabilities. Okay, now I know exactly the distribution of those three, they are independent, and so I can just write an explicit form for this fraction. Okay, and that tells me that this fraction is equal to this term here. Okay, so let's comment just on the first one. That's just what I said. N of A is number of Poisson points in A. The intensity is mu, and so the parameter of this Poisson random variable is mu times the Lebesgue measure of A, which is mu A, and so that gives you indeed this expression mu A at the power m times e to the minus mu A divided by m factorial. That's exactly the probability that a Poisson random variable with parameter mu A is equal to m. Okay? You do the same for the second probability. Now instead of A, you have B minus A using this property, and instead of m points, now you have n minus m, and you divide by same quantity, but now instead of A, you have B, and instead of m, you have n. Okay? So you obtain this expression, and you see that in fact in this expression, a lot of things disappear. Okay? A lot of things disappear. You see that you have a mu at the power m here times a mu at the power n minus m, which combined together give you a mu at the power n, but a mu at the power n in the denominator. Okay, so all the mu's disappear. Okay, and in particular, indeed, you see that here in the result, the intensity mu does not appear anymore. That's where this disappears. Notice also that you have a 1 over m factorial times 1 over n minus m factorial divided by 1 over n factorial. That becomes an n factorial divided by m factorial n minus m factorial. That's an n choose m. That's another simplification. Okay, and obviously a third simplification where the mu again disappear is if you look at those exponential, e to the minus mu a times e to the minus mu b minus a gives you, after simplification, an e to the minus mu b that you find again here, so that disappears. So all the mu disappears and the factorial simplified in some n choose m. And so eventually you can prove that you get exactly this expression. Okay? So let me comment a little bit on that. So you see indeed all the mu's disappeared. I already explained the n choose m. So now to indeed obtain an a over b at the power m, 1 minus a over b at the power n minus m, notice that what's left, after you simplify, you remove everything that depends on mu and have this n choose m, what's left is an a at the power m times b minus a at the power n minus m divided by b at the power n. What I'm doing to obtain this is just that I rewrite this b at the power n as b at the power m times b at the power n minus m, so that the power fits with this one and this one. And then, clearly, eventually you obtain an a at the power m divided by b at the power m. That's a over b at the power m that you have here. And then you also have left b minus a at the power n minus m divided by b at the power n minus m. That's b minus a over b at the power n minus m, but b over b minus a over b simplifies into a 1 minus 1 over b. So that gives you this expression at the power n minus m. All right. So now if you look carefully at this expression, you see that, okay, this is of the form n choose m times a probability, a over b is between 0 and 1, a probability at the power m, times 1 minus the same probability but at the power n minus m. And m and n minus m add up to n here. So this is exactly the probability that a binomial random variable with parameter n, a over b, is equal to m. Okay? So we can conclude that eventually we have that the distribution, like the number of Poisson points in A, given that we have n Poisson points in B, is going to be in fact binomial with parameter n, A over B. Alright, so now we want to prove that this is also equal, to conclude the result, that the cardinal of U intersection A equals M with also this probability. That's going to show that for any possible subset of B, the number of Poisson points in this subset is equal in distribution to the number of those uniform in this same subset. But the fact that this probability is also equal to the probability that the cardinal of U intersection A is equal M is kind of obvious from the definition of uniform. I told you at the very beginning that by definition, uniform here means that the probability that any of those U, let's say Ui, belongs to A is equal to the Lebesgue measure of A divided by the Lebesgue measure of B. That's exactly A divided by B. So each of those n uniform random variables are going to independently fall in the set A with probability A over B. So you have n of them, so n twice, and for each of those n random variables or twice, you have a success probability A over B of falling in the set A. That's exactly the same as a binomial with parameter n, A over B. N, number of twice, that's the number of those uniform, and A over B, that's the success probability, that's indeed the probability that any given of those random variables falls in the set A. The reason why we get binomial, again, we need to underline that, is also follows from the fact that we assume that those uniform are independent. So we have indeed independent twice, and so from that we can conclude that this probability is also the same as the probability that the cardinal of U intersection A is equal to M. Okay? U is the set of n uniform. Alright, so conclusion, what we were able to prove here through this calculation, but it's not that messy, what we conclude is that for any possible subset A of B, the number of Poisson points in this subset is equal in distribution to the number of those uniform random variables in this subset. Okay? That's the conclusion here. Cardinal of U intersection A and cardinal of P intersection A, uniform Poisson, are equal in distribution. That's true for any possible subset A of B. And so from that, we deduce that those n Poisson points and those n uniform are in fact described by the same counting process, okay? Because the number of points in any subset are equal in distribution, and so we can conclude that indeed U and P are equal in distribution. That's the conclusion we have here, and so that shows that indeed the conditioning property is which is well known for Poisson processes, is in fact also true for Poisson point processes in any possible dimensions. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 10 of my stochastic modeling book. That's the chapter about continuous time Markov chain.